Q1, Q2, Q3, Q4 and so on up to Qn charges. To find the total charge Q, I can take the algebraic sum of individual charges. Q is nothing but the charge of a body and N is any integer. What is E here? It's a basic unit of charge. So quantization of charge says that all free charges are integral multiple of basic unit of charge. We know the property of charge that two opposite charges always attracts towards each other. Hello everyone, welcome to session 2 of chapter 1 Electric Charges and Fields. This is Swati, Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, in previous session, we have learnt about the basic concepts of charges and the properties of charges and the concepts which are related to charges and their history. So in today's session, we are going to learn more concepts about charges and their behavior and their properties and many more phenomena. So let us begin with the properties of charges. We know what is electric charge, what are the types of electric charges, what is its basic property, everything. Now we are going to understand in detail about the property of charges. Say for example, they have some behavior, the characters. So how we can utilize the charges as based on their properties, we are going to learn in this session today. So the first property is charges are additive in nature, that is additivity of charge. They are additive in nature, which means we can add each and every individual charge to find the total charge on substance. So next one is the conservation of charge, which means charges can also be conserved. Charges can be added. Charges can be conserved. So the next one is quantization of charges. So these are the three important properties of charges. They are additive in nature, they can be conserved and they are quantized. So what is this additivity of charge, conservation of charge or quantization of charge? Let us see in detail. So first thing is charge is additive. So I'm saying that we can add n number of charges to find the total charge. So the total charge on any system. If we have a system where the individual charges are acting on a system, so to find the total charge on a system Q, we can add the individual charges to find the total charge on any system, says additivity of charge. Say the total charge on any system is equal to the algebraic sum of the individual charges on the system. So for example, I have n number of charges here, Q1, Q2, Q3, Q4 and so on up to Qn charges. To find the total charge Q, I can take the algebraic sum of individual charges. Say I have an example here. So now the charges Q1, Q2, Q3 and so on up to Qn, I have in the expression. So like that I have some values plus 1, plus 2, minus 3, plus 4 and minus 5. So these are the individual charges. So based on this, let us now find out the total charge on the system based on the given data. So now taking the algebraic sum of all these values, the answer will be minus 1. So that is 1 plus 2, 3. 3 minus 3, 0. Again plus 4, minus 5 and the answer is minus 1. So that is the charge on the system based on this data. So this is how we can find the net charge on any system by this property, that is charges are additive in nature. So the second property of charge is charges are conserved, or we can say conservation of charges. What is the meaning of conservation? Which means charges can neither be destroyed nor be created, but it can be transferred from one body to another body. So total charge of any isolated system are always conserved. Say for example, I have two objects and I'm rubbing against each other. What is the phenomena that takes place here in this case is charges will transfer from one body to another body. So here one body is losing some charge, the other body is gaining some charge. Charges are not getting wasted, but it is transferring from one body to another body. So which is meaning of conservation of charge. So it is not possible to create or destroy the net charge carried by an isolated system. So the number of charges lost by one body is equal to number of charges gained by the other body, and hence we can say the charges are conserved in nature. So in example, we can understand this as, here I have a neutron which is decaying as a proton and an electron in this example. So here I have 92 charges which is getting decayed into thorium and helium by splitting its neutron into proton and electron, and we are getting 90 plus 2 here. By adding these two in RHS, we'll get 92. So 92 and 92. Even after splitting, the sum will be 92 itself, which means the charges are getting conserved. They are not wasted. So this is one of the other example to understand the conservation of charges. So next one is quantization of charge, or we can say the charge is quantized. So what is the meaning of quantization? To remember this definition or to understand this properly, we must understand the expression. Q is nothing but the charge of a body and N is any integer. What is E here? It's a basic unit of charge. So quantization of charge says that all free charges are integral multiple of basic unit of charge. So integral multiple of basic unit of charge, that is nothing but all free charges. So we can understand from this expression, all free charges are equal to the integral multiple of basic unit of charge. That is the quantization of charge. Here E is nothing but the basic unit of charge. We know what is the value of this basic unit of charge. The magnitude is 1.6 into 10 power minus 19 Coulomb. So from this, let us now understand what is the amount of charges contained in 1 nano Coulomb. So nano Coulomb means, we know nano is nothing but 10 to the power minus 9. So now from this quantization rule, I can find the number of charges. N is equal to Q divided by E. What is this Q? That is nothing but 1 nano Coulomb value we have. So 1 into nano means 10 power minus 9 divided by the value or the basic unit of charge is 1.6 into 10 power minus 19. So solving this, I will get 6.25 into 10 power 9. So 1 nano Coulomb of charge contains 6.25 into 10 power 9. So this is how we can find the numbers or the values with the help of quantization rule. So basically this quantization method is suitable for a micro level because we can find the number of the charges here in less values like some tens and hundreds, but in case of macro units it is quite difficult and it is not much preferable. So we can also find a charge of 1 micro Coulomb. How much charges it contains? What is the numbers that contains in 1 micro Coulomb of charge? So from quantization rule, N is equal to Q divided by E. What is Q? It is micro Coulomb. Since it is micro, it is 1 into 10 power minus 6 divided by the basic unit of charge magnitude is 1.6 into 10 power minus 19, and solving this we will get 10 power 13 electrons. So 10 power 13 electrons is actually very large amount. So it is macroscopic level. So at macroscopic level, we say that the quantization charge has no practical consequences and hence it is preferable only in microscopic levels. So these are the basic properties of charges. So we have come across what is charge, what are the behavior of charges, what are the basic properties of charges. Now what is the SI unit of charge? The SI unit of charge is Coulomb, or it is denoted by the letter C. So what is the difference between this mass and charge? Are they same? So mass is always positive, but we have charges as two categories. It may be positive or negative. The mass of a body can be increased when the body is charged negatively. So there are few differences between masses and charges. They are not same. So let's move on to the next topic, that is Coulomb's inverse square law. It is very important examination point of view. So Coulomb's law basically gives us an idea about the force between two charges separated by a distance. It is quite similar to Newton's law of gravitation with the masses, but here Coulomb's law says about the charges, or it defines about, the law gives us an idea about the force between two charges separated by a distance. So let us now see the statement. So what is the statement of Coulomb's law? The force between 2 point charges, force between 2 point charges is directly proportional to product of magnitude of two charges. The term product of magnitude is very, very important. It is directly proportional to product of magnitude of two charges, and it is inversely proportional to square of the distance between two charges. Here also the term square is very important. Students, while writing the answer in examination, most of you will forget to write square and product. So these are a very, very important terms which you should not forget. So the statement is very important before going to arrive at the expression. So square of the distance between two charges acted along the line joining two charges. Say for example, I have two charges Q1 and Q2. They are separated by a distance R. Then according to Coulomb's law, force between these two charges is directly proportional to product of magnitude of two charges. So what is the magnitude? Product of magnitude of two charges. I have Q1 and Q2. So since I am talking about the magnitude, I have to denote this with the modulus, and here I have product. So product of magnitude of two charges, and it is inversely proportional to square of the distance between them. What is the distance between these two charges in this scenario? It is R. So square of the distance, that is R square. So this is Coulomb's law. Let us write an explanation for Coulomb's inverse square law. We have Q1 and Q2. Those are the point charges. They are separated by a distance R. And what is F? F is nothing but the force between two charges. Then as I explained, according to Coulomb's law, F is directly proportional to product of magnitude of two charges, and it is inversely proportional to square of the distance between them. So now this proportionality can be replaced by a constant, and I'll take it as K. So F is equal to K into Q1 Q2 divided by R square, where K is proportionality constant. So the value of K depends on the system of units what we consider. So in SI system, we have the value of K as 1 by 4 pi epsilon naught. So what is epsilon naught? It is permittivity of free space. What is permittivity of free space? It is nothing but the ability of charges to pass through the surface in a vacuum. Now we are talking about, that is why the name free space. So epsilon naught is permittivity of free space, and by applying the values or by substituting the values of pi and epsilon naught, we can find the value of K, and the value of K is calculated as 9 into 10 power 9 Newton meter square per Coulomb square. So what is the epsilon naught value? The epsilon naught value is 8.854 into 10 power minus 12 Coulomb square per Newton per meter square. So this is about Coulomb's inverse square law. So basically, Coulomb's square law or Coulomb's inverse square law says about the force between two charges separated by some distance. So now from this, we can write the expression for force between two charges, that is F is equal to K into Q1 Q2 divided by R square. So what's the value of K? F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. So with the help of this expression, we can find the force between any two charges separated by some distance, and we are going to use this formula in most of our upcoming derivations in our next classes. So let us now understand the pictorial representation of force of repulsion and attraction between any two point charges. See, in the first case I have taken two opposite charges. We know the property of charge that two opposite charges always attracts towards each other. That is why the direction of force of attraction is towards each other, because there is a force of attraction between these two charges. And here in this case, you can see I have taken two like charges. So like charges always repels each other, and that is why the direction is outwards, because here we can observe the force of repulsion. So here positive F and it is negative F, which means they are opposite in direction since they are undergoing repulsion. So this is about Coulomb's inverse square law. We know what is the unit of charge. It is Coulomb. So let us now define what is 1 Coulomb. How to define the unit of charge. How to define 1 Coulomb. So 1 Coulomb is the charge when placed at a distance of 1 meter from any other charge of equal magnitude or the same magnitude in vacuum experiences an electric force of repulsion of magnitude 9 into 10 power 9 Newton. Here, to remember this statement, we must go through these steps. So that is two charges I have, Q1 and Q2. They are of same magnitude, that is 1 coulomb, and they are separated by a distance of 1 meter. And substituting all these values in our expression, F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. So now Q1 Q2 is nothing but the value of this will be equal to 1, and the value of R square is equal to 1. So these two will cancel, or it will be 1 again. So I remain with F is equal to 1 by 4 pi epsilon naught. So what is the value of K, or 1 by 4 pi epsilon naught? It is 9 into 10 power 9. Since we are calculating force, it is Newton. So 1 coulomb is the charge when placed at a distance of 1 meter from another charge of same magnitude experiences a force, electrical force of repulsion of magnitude 9 into 10 power 9 Newton is nothing but 1 coulomb definition. So in the previous expression, I have used the term 1 by 4 pi epsilon naught, and epsilon naught I told you it is permittivity of free space. So how to define this? What is permittivity of free space? So let us now understand. So permittivity is nothing but the capacity or the ability of the medium that allows the charges or the electric field lines to pass through the medium is called as permittivity. So if I say about free space, it is for vacuum. So permittivity is defined only for insulators, or we can also say the insulators as dielectrics. So permittivity of free space or permittivity is the ability of medium to allow the electric field lines to pass through it, and the permittivity is defined only for dielectrics. So by knowing the definition of permittivity of medium or free space, we can find the relative permittivity. So what is relative permittivity? So let us see now. Considering two charges Q1 and Q2, they are placed in free space, or we can say in vacuum. Like we have two charges Q1 and Q2 in vacuum, and they are separated by a distance of R. Then from Coulomb's law, we can write F alpha. Because in free space, I have taken it as alpha. F alpha is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. That is our equation 1. So now when these two charges are placed in dielectric medium other than the free space, any other medium, dielectric medium if we consider, then we can write Coulomb's law as Fm. M means the medium, 1 by 4 pi epsilon. You can observe here there is no naught. Epsilon naught is only for free space. Epsilon is for dielectric medium. So 1 by 4 pi epsilon Q1 Q2 divided by R square. That's my equation 2. So taking the ratio of these two equations, the common terms will get cancelled. That is 1 by 4 pi and 1 by 4 pi will get cancelled. Q1 Q2 by R square, Q1 Q2 by R square will get cancelled. And we remain with epsilon divided by epsilon naught, which is equal to epsilon R, where epsilon R is nothing but the relative permittivity. So knowing about the definitions of relative permittivity and permittivity of free space are very important, and knowing about the meaning of the terms epsilon, epsilon naught, epsilon R is also important. We must also understand few important points, that is dielectric constant or relative permittivity has no unit and no dimensions, and also the value of dielectric constant depends upon the temperature. The value of the dielectric constant is always dependent on temperature. So dielectric constant is also called as specific heat capacity of the medium. The specific capacity of any medium can be also calculated with the help of dielectric constant. So these are the few important points regarding dielectric constants. So going forward, we have to deal with the superposition principle and Coulomb's law in vector form. So to understand all those derivations, we must understand about few concepts which we have already studied in our first PUC. Among that, first thing is a unit vector. So what is a unit vector? What is its significance? A unit vector is a vector whose magnitude is always 1. So unit vector is also known as a direction vector, because that is the significance of unit vector. It will give us an idea about the direction. So unit vectors, which is equal to vector divided by the magnitude of vector. So if we solve this, we will get the magnitude is always 1. And unit vectors are commonly used to indicate the direction, and hence they are called as direction vector. And also we have a position vector. Going forward, we need to understand the difference also between the unit vector and position vector. What is a position vector? A vector drawn from the origin. So you can see here, any vector that drawn from the origin to the position of a particle at any instant is called as a position vector. It will give us an idea of position of any particle from the origin. If it is drawn, then it is a position vector. So position vector is used to tell how far and in which direction the point is with respect to the arbitrary chosen origin. So about these two vectors we have already studied in your first PUC. Difference between unit vector and position vector you must know, and you must also know how to draw position vector, how to indicate position vector in plotting the positions of particle with respect to origin. So unit vector is always denoted by cap and position vector is always denoted by the arrow mark on top of it. So this is about the basic properties of charges, where in this session we have learnt about the properties of charges such as they are additive in nature, they are conserved, they are quantized, and also we have understood the Coulomb's inverse square law, and also we have learnt about the types of vectors which we are going to use in writing the expressions in upcoming sessions. So in the next session we will learn about superposition principle, Coulomb's law in vector form, and many more important concepts. Until then, keep learning all of you. See you all in the next session. Thank you.